Yeah, it's a pleasure to be here today, back in Sydney, and speak to you about what I've been looking at for my PhD for the past couple of years, which has been in analog quantum simulators. So first off, I just wanted to take a step back and draw some similarities and differences between analog and digital systems. So often in quantum devices, we might be able to make this distinction, and in the analog case, we might consider some Hamiltonian model that models a system that we're interested in, say electrons moving in a solid, or vortices in a BEC, or some chemistry problem, or some network problem. And in an analog quantum computer, what we aim to do is implement that Hamiltonian and the rule set of that Hamiltonian directly, and then starting with some initial conditions, some initial wave function, we want to continuously evolve that system under the Hamiltonian and then read out the resulting states and then analyze that system directly. And the merits of this system is that it's very powerful. It makes use of the resources that we have available quite efficiently. However, it's not universal. If you have a certain Hamiltonian, it's not going to necessarily be able to help you answer questions about other areas of physics. However, in the digital side, which is something you might be a little bit more familiar with, in order to understand these areas of physics, we might want to approximate these sorts of Hamiltonians digitally, whereby we break down what's going on into physical qubits, sort of the simplest quantum system, a two-level quantum system. And we say if we want to consider time evolution, we would break that down, trotterize that, for example, and break it down into small time steps and approximate the whole solution digitally. And the merits of a digital quantum computer are that if we're able to build one, it would be universal, able to model any sort of quantum problem. However, it is quite resource intensive. Say if you wanted, in an analog case, to model 4 atoms, you're probably going to need more than 4 qubits in order to do that. Obviously these systems are still being developed. But I think just to draw another comparison between these two systems in a classical case, say in a classical problem, if I consider a one-dimensional string and a wire, and I want to bend it in some random configuration, and if I want to solve what's the minimum 2D surface area that covers this one-dimensional string in 3D space, turns out that computationally is a very, very difficult problem to solve. On a digital computer. However, if I took this string and I shook it in some bath water and then I brung it up, then instantaneously I would have a nice soapy film that covered this string. So in this particular example, this bath water is acting as an analog computer and instantaneously solving this very, very complex problem. So I think in the quantum case, a lot of the questions that we're interested in answering about dynamics and ground states is sort of we can answer with potentially with both analog and digital systems. And I think what runs out, although some people might disagree, is maybe the questions that we're asking and sort of the efficiency of the computers that we have available. Now I want to talk about the system that I have been looking at quite closely in my PhD, which is a particular analog quantum simulator called an optical lattice. And what we do is we create standing waves of light with lasers, and we orientate these in different angles relative to each other to create different sorts of two-dimensional and three-dimensional standing waves. And then we load atoms, ultra-cold atoms, bosons or fermions into this lattice. And due to the light-matter interaction, these atoms essentially feel a force to the minima of the standing wave. And what the atoms see is that they are confined and described quite well by a Hubbard model. And a Hubbard model is something that we've stolen from condensed matter, which describes the movement of electrons in a crystal. If you have an electron, it might be tightly confined to a nucleus, but sometimes it has the opportunity to hop to neighboring nuclei. And the energy cost of this hopping process we can characterize by this tunneling amplitude J. And then if you have, say, 2 electrons coming into contact with each other on the same nuclei, then they might interact with some interaction energy U. And in this sort of synthetic Hubbard model that we've created with this optical lattice, we essentially engineer the exact same Hamiltonian. Where we, here we have this Hamiltonian for bosons. The Bose-Hubbard model, where we have the summing over nearest neighbors, Ij, and then we also have this interaction energy, U, and then we have a quite similar Hamiltonian when we load the system with fermions, and the interaction term is slightly different because we're now dealing with the Pauli exclusion principle. We can not only simulate Hubbard models in the optical lattice, but we can also simulate spin lattice models, and we can do this by loading the lattice with two species of atoms, say called an A and B. And in a regime called the Mott regime, where the interaction is very, very large with respect to the tunneling amplitudes J, then the atoms are essentially confined to each lattice site, and they're restricted from tunneling because if they were to do so, then they would have to pay this energy penalty of having, say, 3 atoms on one site, and this is energetically very costly. However, there's a second order process whereby an atom might tunnel to one site and a neighboring atom might tunnel back. And if we consider this tunneling term as a perturbation and characterize the Hamiltonian in a spin basis where we consider that occupation numbers of these two different atoms, A and B, we can model this on a sort of like proxy block sphere. And if we look at this resulting second order perturbation under the spin basis, then we can construct this spin lattice Hamiltonian here on the right-hand side. And this in particular is XXZ Hamiltonian, but we can turn this into, in Heisenberg interactions, if we set this lambda z to be equal to this lambda perpendicular, which we're able to do by adjusting the sort of lattice parameters. We can also create XY interactions by setting this lambda z to 0, and we can create Ising models, etc. So we can also simulate these spin lattice models with the optical lattice. And then once we build these Hamiltonians, we are able to take projective measurements of the system and see how it evolves in time in order to solve one of the most fundamental equations in quantum physics, which is the Schrödinger equation governing the time evolution of the system. And we can use this in order to assess the dynamics of the system and answer questions in seemingly very different areas of physics. So the first implementation of an analog quantum simulator was about 20 years ago, where they showed this phase transition between a superfluid and a Mott insulator. But we can also study different aspects of physics, for example, high-energy physics. Here in this experiment, they created some density-dependent gauge fields. Also, topological physics, we can build topologically non-trivial band structures and study things like topological insulators and quantum Hall physics and general topological order. And also things like quantum thermalization in closed systems, the ETH, and even things like cosmology. We can study Kibble-Zurich mechanism. This paper was doing a simulation of the false vacuum decay of the universe. So so there's lots of exciting experiments and simulations that we can do to many different areas of physics just by using this sort of synthetic Hamiltonian that we can control very precisely. And so with these optical lattices, traditionally, they have been very, very good at modeling systems with global parameters, where we have some global tunneling J and some global interaction U that is the same wherever you are in the lattice. However, it would be very nice if we were able to locally tune the parameters of this Hubbard model. And so, in particular, tuning this local tunneling has been what I'm going to focus on for the remainder of this talk and what has been one of the main focuses of my PhD. And in order to achieve this, we want to utilize a technology that's been developed in the past 10 years, which is a quantum gas microscope and an optical tweezer. And Kavya talked a little bit about these optical tweezers yesterday in the context of Rydberg atoms. But firstly, this quantum gas microscope, what it is a high aperture numerical lens that we put underneath the lattice. and it enables us to image single sites of the lattice. So on the left-hand side, you can see this. We take projections. We can see where the atoms are by shining light from the top and then see where the shadow is. And this is a picture, essentially, of atoms on the single site level. And we can use this to build up, do tomography and build up a picture of what's going on in the lattice and do sort of correlation functions and things like that. And then if we were to shine a new laser through this optical tweezer, then, through this quantum gas microscope, we can create something called an optical tweezer, which is a very, very tightly focused new potential on top of the optical lattice. And we can use this to generate new potentials in the lattice scheme and generate Hamiltonians that are locally, that are different locally in different parts of the lattice. And what we wanted to do is combine this technology with an idea of flow K engineering. So we wanted to explore what would happen if we were able to shine these local potentials to different parts of the lattice, and what would happen if we drove those potentials, and what sort of utility would that give us over the Hamiltonians that we're able to engineer. So just to briefly describe flow K engineering, flow K theory dates back to work of a mathematician back in the 1800s who studied the solutions to differential equations when you have periodic coefficients. So just to draw on some intuition you might have of Bloch's theorem, so when you have a Schrodinger equation, which is a differential equation, and you have some periodicity in space, then there are certain things that you can say about the solutions of that equation, namely that they are Bloch waves. Where you have some component of that solution which has the same periodicity as the lattice structure A, and then this is multiplied by some phase. And so if you were to look at the solution of the Bloch wave only in units of your lattice constant, then all you see is this phase. And similarly, flow K theory is the idea that if you have a Hamiltonian that is periodic in time, in a similar vein, the solutions to that, the time-dependent solutions to that are flow K states, where you have a periodic component U, which has the same periodicity as your underlying Hamiltonian, capital T, and then multiplied by some overarching phase. So this means that if you were to look at this time-dependent system stroboscopically in units of your drive, capital T, then all you see is this phase. And that means that you can look at the system as evolving under a new time-independent stroboscopic Hamiltonian, which I've labeled HST0. And importantly, this new time-independent stroboscopic Hamiltonian might have qualitatively very new features relative to the time-independent Hamiltonian. And basically, by utilizing flow K engineering, we can generate all sorts of different stroboscopic Hamiltonians that have new features that we would like to generate. And it essentially extends the toolbox that we have for generating different Hamiltonians. And there are many systems, say, like flow K topological insulators, which are only able to be only accessible by flow K engineering. And in the case of cold atoms and optical lattices, flow K engineering is a technique that's been extensively used because we have very precise control over the parameters and we can change them in time. So it's a natural system in order to realize flow K engineered systems. So just to give some history, so the first experiment along these lines was done in around 2007, where they drove a whole lattice and showed that when you drive a whole lattice, it renormalized the tunneling amplitudes and your engineered stroboscopic Hamiltonian to follow a Bessel function, where the argument of the Bessel function is the ratio between the drive and the frequency. And the idea that you generate zero tunneling at certain frequencies of the drive is this idea of dynamical localization. You can shake the system and make everything stationary. This was also extended in another experiment where they drove the system with a function that broke time reversal symmetry, and in that case they can imprint Peierls phases in the lattice. And this is also done in two-dimensional systems where they use laser-assisted tunneling and in order to imprint artificial gauge fields on the lattice. And so now just to get into sort of the machinery that we use to study the flow K, these stroboscopic Hamiltonians under different driving conditions. So it turns out that these flow K Hamiltonians are very difficult to calculate analytically because they involve time-ordered integrals of Hamiltonians that don't commute with each other. However, we can calculate them numerically just by taking some basis states and evolving them under the full time-dependent Hamiltonian and then constructing the time evolution operator and then using that to see what our engineered phase and therefore our new stroboscopic Hamiltonian is. However, these stroboscopic Hamiltonians are T0 dependent. They depend on the initial condition that you choose. And for each T0 in your driving period between 0 and T, you have a different stroboscopic Hamiltonian. These are all related by some gauge transformation. And so this T0 dependence is not so ideal, and it turns out that we can change basis and effectively make a gauge transformation into a frame where this Hamiltonian has no T0 independence, and this is called the effective Hamiltonian. And this is quite convenient in order to study the long-term dynamics of the system. And conveniently, there turns out to be some analytical expansions that we can use to approximate this effective Hamiltonian. And these involve, as the left-hand side equation with the yellow box, a sum of terms where we have increasing orders of inverse the driving frequency. So this is sometimes called the high-frequency expansion. It's related to the Magnus expansion, if you're familiar with that. And this is quite useful in the context if we're driving a system with a frequency that is quite high, then we can characterize this Hamiltonian by the first couple of terms of this expansion. And on the right-hand side, just to give an example, if we have a Hamiltonian where we have homogeneous tunneling J across the lattice, but say we are using these tweezers to drive the local chemical potential of the lattice in a time-dependent way, where we're defining the amplitude of this drive in different sites of the lattice, then utilizing this high-frequency expansion, this generates the first order, an effective Hamiltonian where we've renormalized the tunneling to a Bessel function, where the argument of the Bessel function is the difference for each tunneling to neighboring sites is the difference in the drive amplitude between those neighboring sites. And conveniently, the second order component is 0, so this means that this first order component we hope to be quite an accurate representation of what we're going on if we have reasonable drives. So just to give an example of this, put this into a context, say if we have quite a simple system, a one-dimensional lattice, and say we drive only a single site labeled B with the amplitude A and some frequency omega, then we would expect, because there's only non-zero relative modulation between the sites neighboring B, then we would expect under this renormalized effective Hamiltonian, we would only engineer a renormalized tunneling in these neighboring elements, and this will be renormalized with the Bessel function relative to the size of the amplitude and the frequency. And we can verify that this works by numerically calculating the stroboscopic Hamiltonian for some choice of T0, and we can show that this matrix element, which characterizes this tunneling, also follows this Bessel function as we would expect. And this is just a representation of the stroboscopic Hamiltonian, and the off-diagonal elements give us our tunnelings, and we can see that only the nearest neighbor tunnelings have been renormalized. The stroboscopic Hamiltonian is quite useful to analyze all the higher order effects of the system. So say if we look at the same Hamiltonian on a log scale, we can see that there are some long-range tunnelings that have been introduced, and these are a product of these higher order terms that we're not considering in this first two terms of this analytical expansion. However, if we have large enough driving frequencies, then we can make sure that these are very small. And now to look at something slightly more practical, if we wanted to if we want to have control over a single link in a one-dimensional chain, then we can utilize the fact that it's only relative modulation between neighboring sites that induces some renormalization. And if we were to drive all sites on one side of this chosen link, then we would expect that we would only engineer this renormalized tunneling in this chosen link. And we can verify that this works by calculating this stroboscopic Hamiltonian. And we can see that it follows this Bessel function behavior. And so just extending this in one dimension, it turns out that we have full control over the tunneling elements in one dimension because we can always choose, starting from the left-hand side, we can always choose driving elements on the right-hand side to be such that we engineer the right tunneling that we like in the specific J prime. And then moving down the chain, we can just add different driving functions in order to generate a completely bespoke one-dimensional chain of tunnelings. And just to put this into context, into some interesting models, so we can use this to generate a model called the Sushri-Fahiga model. Why do we want to create this model? It's an interesting, the simplest topologically non-trivial model in one dimension. It has edge states, and it's characterized by alternating tunnelings, J prime, J prime prime, J prime, etc., along a one-dimensional chain. And we can generate this using this protocol by choosing driving amplitudes such that the relative change between sites alternates between two different values. And in our renormalized case, we get this effective Sushri-Fahigan model. And we can verify we can do this by calculating this stroboscopic Hamiltonian. We can see that the tunneling alternates between two values, and we can calculate behavior of this model and calculate things like edge states and see that they behave in the way that we expect. We can also quite naturally, with this scheme, extend to higher-order SSH models like SSH3 and SSH4 models, and these are characterized by repeating tunneling elements that follow a period 3 or 4 sequence, respectively. So, and we can do this just by choosing our driving amplitudes in such a way that the relative changes in some period 3 or period 4 sequence. And this is something that would be impossible to do with sort of a stationary optical lattice, but it is something that we can quite easily do with this local modulation scheme. Another application of this is simulating black hole physics, crazily. So it turns out that some clever quantum gravity people have found a mapping between the curved space-time, the dynamics of quantum particles in curved space-time and a Hubbard model in one dimension. So if you take the curvature of space-time that you expect around a black hole, if you couple that, if you look at that in Eddington-Finkelstein coordinates where you have no singularities, where you're looking, and if you couple that with the Klein-Gordon equation describing the motion of quantum particles in a relativistic setting, and then if you discretize the solutions of that, then it turns out that the Hamiltonian that governs those dynamics can be modeled by a tight binding chain where you have tunneling that linearly goes from a positive to a negative value. And another intuition for this comes from the fact that if you look at the light cone as you move towards the black hole horizon, the way that it shifts and compresses is the same as the way that the local dispersion relation changes and shifts as you move along a one-dimensional chain where your tunneling is moving from positive to negative in this way. And so, we can encode this black hole geometry into these tunneling amplitudes, and we can do this effectively by using this local driving. So how we do this is we reverse engineer this Bessel function to choose driving amplitudes on neighboring sites such that the difference in the amplitudes gives us, in a renormalized case, gives us these tunnelings that follow this linear relation. And we can calculate this in the stroboscopic case and see that this works, and we can create these stroboscopic Hamiltonians that follow this linear profile. And then we can model the behavior of particles under this under this model. And so on the left-hand side, where we have a lattice that has just homogeneous tunneling, we can see that if the y-axis is time, if we start a single particle, we see the ballistic expansion of that particle. However, if we induce this linear tunneling profile, then we can see that the particle approaches as it approaches the event horizon, a small amount of it is radiated out. And we can characterize the temperature of the black hole by diagonalizing the system outside the event horizon, seeing that it is thermal and characterizing the temperature. We can see that this corresponds to the temperature of the black hole that we've encoded, which corresponds to the gradient of the tunnelings that we've encoded into the system. We can also extend this to a 2D setting and create a 2D black hole by first by engineering tunnelings that for any radial profile, any radial line out from the center of the black hole out towards the event horizon follow the same linear relation. And so, yeah, we can initially do this for a stepwise movement along the 45 degree, and then we can smartly fill in all the different amplitudes that we need to ensure that any sort of stepwise walk in some radial direction gives us some linear tunneling metric. And this would encode a two-dimensional black hole. Please just interrupt if anyone has any questions. Just to move on to another example in 2 dimensions. We looked at how we could utilize this local driving in the context of a lattice called a Lieb lattice, which is essentially a square lattice with slightly less connectivity, or 3 sets of sublattice square lattices, where we've indexed one of the sublattices by black circles and the other 2 by these orange circles. And why is this useful? Well, firstly, if we represent this Lieb lattice on a Hamiltonian, then this is how it looks if we just have, before we start driving, then if I just plot my matrix elements in this way, this is what this Hamiltonian looks like. However, if I were to drive just a single site in one of the orange sublattices, the site 7, then I can renormalize just one link in this in the black sublattice in a controllable way. And I can extend this and drive all of these orange sublattices in independent ways in order to control the effective tunneling between my black sublattice sites. And in this scheme, we can realize essentially an effective 2D square network with controllable tunnelings between these black sublattice sites. And we can characterize the tunneling between the black sites by the second order tunneling in the full Lieb lattice system. Yeah, so another useful aspect of using flow-K engineering is the creation of complex tunneling amplitudes. So this is something that we're not able to do by any other means. If we have a stationary Hamiltonian, we're not able to generate any kind of complex tunneling. And in 1 dimension, this doesn't matter and this has no physical significance. So in 1 dimension, if you have complex tunnelings, say you tunnel from one site to the next and you pick up some phase, then if you have a Hermitian Hamiltonian, then when you tunnel back, then you necessarily have the inverse phase, and therefore this particle will never interfere with itself as with some non-zero phase, because as it tunnels one way, it picks up the phase, and it tunnels the other way, it loses it. However, in the context of a 2-dimensional system, sometimes these phases can become significant physically. So in the case of a 2-dimensional lattice, if I pick up some factor of phi going around a plaquette, as I go around the full plaquette, the relative wave function has a phase difference. And then this can engineer some synthetic flux, because this might remind you of what happens when you have an electron moving around a magnetic field. Then the electron will pick up a phase that is relative to the magnetic field, a flux of the magnetic field that it encloses. And so in this way, if we're able to engineer complex phases on tunneling elements, then we can simulate things like, we can synthetically simulate things like magnetic fields, even though we're dealing with neutral atoms. And just to look at this closely, so in a simplest possible case, we wanted to see what sort of control that we have over the relative tunnelings and also the plaquette flux in the simplest 2D system, i.e. a 2D triangular plaquette, just by driving two sites of this plaquette by these two different functions, where the site 2 we drive by amplitude A2, site 3 by amplitude A3, and slightly different tunneling frequencies, where we have this base tunneling frequency omega naught, but site 2 is driven by alpha omega naught, where alpha is some integer, and also beta omega naught characterizes the driving frequency of site 3. And when alpha and beta are integers, this means that there's some overarching period of the system characterized by omega naught, and we can utilize Foucault theory. We also include that the third site might be offset by some phase relative to the second site. And we wanted to look at, under this toy model, what sort of control do we have over the three renormalized tunnelings, and also the flux that pierces this plaquette. And just firstly looking explicitly at the renormalized tunnelings that we get in the high frequency expansion. So between site 1 and site 2, we just have this normal Bessel function, because the relative shape between these two neighboring sites is just a cosine function, and the same thing between site 1 and site 3. However, across site 2 and site 3, we have this summation of these two phases, these two drives, and one might be out of phase with each other. And if this drive, the sum of these two functions breaks some time reversal symmetry, then we have the opportunity to engineer a complex tunneling element across this site 2 and site 3, which is characterized by this two-component Bessel function. And just to firstly analyze what control we have over the relative tunneling amplitudes. So if we, under this system, if we order the three renormalized tunnelings by the smallest and the largest values, and if we plot the ratio of these values on this xy plane, then this ratio point will always fall in this lower triangle of this unit square, where up the top right-hand side, this corresponds to a ratio of 1, 1, 1, where they're all the same. And we show that we can cover this whole triangle just by changing the parameters of this drive. And so on the left-hand side, the color in the left-hand plot shows the A2 value to achieve that particular tunneling ratio, and the right-hand side shows the A3 value. So you can see that top right-hand corner, when we have these are both green, and that corresponds to the fact that if we don't drive the system, then we have a ratio of 1, 1, 1 between all the driving elements, and then we can achieve any desired ratio between these elements just by adjusting these driving amplitudes. But yeah, we also wanted to know what control we have over the flux, and do we have full control over the flux independently to these relative driving amplitudes? And to answer this question, we utilized a numerical optimization program, so where we would choose a specific tunneling ratio. So in this example, we've chosen a ratio of 0.5, 0.3, 0.1. And using a numerical optimization tool, we calculated for some target flux what the A2 and A3 and offset phase var-phi values would be in order to generate these, not only this target flux, but also this relative tunneling amplitude. So here on the left-hand side for this target flux, on the x-axis, we show the A2 and the A3 and the var-phi values that would achieve this target flux by keeping this, but also keeping this ratio constant. And on the right-hand side, we show the absolute value of these tunnelings, and they keep some constant ratio. And yeah, another application of this, another way that we can generate these complex elements in a two-dimensional system is utilizing something called laser-assisted tunneling. So sometimes if you have in the lattice some local chemical potential of a neighboring site relative to its neighbor, then if this local offset is very, very large, then you can reduce the tunneling that is achievable between these two sites, because the atom would have to pick up enough energy in order to tunnel, and it might not have that energy. And however, we can restore tunneling by driving one of the sites with some modulation frequency that is resonant with the offset. And in that case, the atom can pick up some phonon from that drive in order to restore tunneling. And it turns out that if we combine these static offsets with this time-dependent drives, we can generate a new Hamiltonian, effective Hamiltonian, where we engineer a new a phase where this phase chi is relative to is set by the relative phases of the initial the drives of the initial Hamiltonians on these neighboring sites. And we can control this by changing these relative phases in conjunction with this usual Bessel function behavior that we've seen. And as an example, we wanted to show how we can use this to generate a magnetic field gradient in 2D. So here's just sort of like a particular application of this, where on the top row, if we have the local chemical potential, all the top row being 0, and then all the bottom row being omega relative to the top row, then this means that all the vertical tunnelings will be renormalized by this function, and we have the opportunity for them to become complex if we choose these offset phases in the right way. However, all the horizontal tunneling is going to be real because there's no relative static offset, and so it's going to be renormalized by the Bessel function as we saw previously. So yeah, by choosing smart choices of these phases at certain sites, we can engineer a system where the plaquette flux as you go around a full plaquette changes as you move down the lattice in the x direction. And here's just an example where we've engineered fluxes that follow some linear pattern. And we can verify that this works numerically here's just a numerical simulation of this on a 20 × 6 system. And here we've shown the plaquette fluxes of the system by the color bar, and we can engineer these to change in a linear way. Yeah, so that's sort of the end of the applications of this system. So yeah, in summary, we can, there's many ways that we can utilize these local drivings to engineer not just relative tunneling shifts, but also these phases, and we can engineer all sorts of interesting systems like magnetic fields, or SSH models, or black holes. And I also just wanted to make a point about universality. So at the beginning, I said that one of the drawbacks of using these analog quantum simulators is the idea that they are not universal. But I just want to make the point that there's some work done on some complexity theory. People have been looking into the fact that just because you have a Hamiltonian, it doesn't mean you're not able to. Sometimes that Hamiltonian might be able to help you understand many other different types of Hamiltonians. So in this paper by Toby Cubitt, he using some sort of perturbative gadgets, he shows that just with nearest neighbor Heisenberg interactions and nearest neighbor XY interactions, this can be used to simulate many other different types of Hamiltonians, even with long-range interactions or other types of symmetries, or higher dimensional spins. And there's sort of some cute little gadgets that you can use to transform analog simulators into the other analog simulators. But in particular with this claim that he makes, that what is required is these nearest neighbor, the local tunability of these nearest neighbor Heisenberg interactions. So clearly, being able to locally tune the parameters of these analog simulators is going to help us in order to create these simulators that are more universal and able to access the physics of lots of different other systems. So yeah, in summary, we've been looking into how local periodic driving using these optical tweezers and quantum gas microscopes allows us to construct these new Hamiltonians with locally tunable parameters. So in one dimension, we have very, very good control over the resulting systems. We have full control over the size of these tunneling amplitudes, because flux doesn't matter, or so complex elements don't matter because they're not physically significant in one dimension. Then that means that you can model with an optical lattice any sort of one-dimensional system that you can write down, assuming that it only has nearest neighbor tunnelings. And then in 2D systems, there's lots of different very interesting models that we can create. In a Lieb lattice, we can create a programmable 2D network. We can create a 2D black hole Hawking radiation simulator and magnetic fields. And then I think a next step with this is extending this full control that we show in a triangular paquette to larger systems. And in the triangular paquette, it was useful to utilize numerical techniques in order to achieve sort of target parameters, any sort of target parameter that we set. And if we extend this to larger 2D systems, it would seem that the number of degrees of freedom that we introduce in these drives extends in a favorable way relative to the degrees of freedom in the new effective models. So it seems likely that we would be able to fully control systems in 2D, but yeah, this is a work in progress. And yeah, I'd also like to thank my collaborators, my supervisor, Ulrich, Aydin, Asme, and Yanis, who are black hole experts, and Noor, who works in condensed matter. And yeah, thank you so much.
Some questions. Tom.
Thanks, that was really nice. With the magnetic field gradient, that is effectively a classical magnetic field, and it's specified by some external control field, if I understood. Do you have any idea how you can make the effective magnetic field itself dynamical, so that you could, for example, simulate composite bosons?
Yeah. So make it dynamical. I think there's probably a way. So if you were to, potentially if you change this time-dependent Hamiltonian in such a way that over the first period you generated some effective Hamiltonian in the first instant in time, and then maybe if you change that for the second period to be something slightly different, that corresponded to a different Hamiltonian for your second period in time, then maybe that would work. But maybe if you were able to, because we have very good control of all of these driving parameters, and we can change them in a time-dependent way. But the fact is that the sort of effective description comes from effectively what happens over one period. So yeah, maybe there's a way that you can sort of, in a time-dependent way, change this periodic modulation, and you can maybe sort of like split up what you're talking about into some like discrete change, and you have one magnetic field one time and then another magnetic field another time, and you could, if you're happy to sort of set that in some discrete way and then change your time dependence in that way, then maybe that would be possible, yeah.
So that would give you a time-dependent magnetic field that would be a pre-specified schedule. What I'm saying is that if you, say you had a objective time-dependent magnetic field and you broke that down into, say, like a number of steps, then say over the first period, you set your parameters to be such that over that period you generated your first step in your magnetic field and then the second step. So you have to discretize it, I think. So I think I'm asking a slightly different question, which is can you see a way that you could, rather than having just a preset schedule for what the magnetic field is locally, that it becomes its own dynamical degree of freedom that couples to the lattice?
I'm not sure what you mean by that. Okay, maybe we can talk after, yeah.
Any more questions?
think your first slide you had a picture of a 3D optical lattice.
Yes.
So can you say anything about how any of these techniques might?
Yeah, so the theory of this sort of effective Hamiltonians, doesn't, can be extended to these 3D systems, because really what is happening is that this renormalization comes just summing over nearest neighbors. So effectively all the same rules apply. So if you were to drive to nearest neighbors in some way, then you can characterize this renormalization. Yeah, you can do it in 3D. I haven't looked at any sort of specific applications, but the theory of this extends to that, yeah.
But you need this local addressability.
Yes, yeah.
And that probably is.
So I think it's a different engineering problem for the lattice to sort of locally focus. Though I think it's possible, but to sort of calibrate that I think would be quite difficult, but probably not impossible.
Thanks, Georgia. So I was just wondering if you could comment on kind of like this experimental prospects for these kind of things. Like, you gave this very nice summary at the beginning, and there was a lot of excitement in the field in 2002, and the first kind of Greiner observations were made, and then I feel as though everything was a bit harder than everyone thought, and that there is, you were mentioning a lot of recent experiments in the last few years, and so I suppose I'm just wondering, like, what do you are you optimistic about implementing this or other similar schemes and experiments? And is this going to be a rapidly moving experimental topic?
Yes. I think so. In the lab that I'm working with at the moment, they're sort of in the stage of sort of characterizing these like optical like tweezer potentials, and sort of and sort of trying to figure out the best way to, because you do have these, there are all sorts of experimental imperfections that come in. I think that the biggest challenge is bokeh heating. So, but I think the timescales of these things are long. So even just to build an optical lattice takes like a number of years in order to like calibrate the lattice. And so these tweezers have been used in other contexts in the case of Rydberg experiments, and they've been shown to successfully engineer these interactions in that way. So I think there's no reason why they can't be used in a slightly different context. So the calibration that's involved, I think, will take a number of years. But so it's kind of, in the lab that I'm working on at the moment, it would have been great to sort of have an experimental result, like in conjunction with the theory work that I've done. But I think, the reality of the experiment is that it takes a long time to calibrate things. But it's really hard to know exactly the time scales. But I think it's possible. I think that the biggest hurdle will be the heating.
Question at the back, Sandra?
Yeah, I think kind of following on from Andrew's, I'm not very familiar with the optical analytic systems, but I was going to ask, like, have you done any simulations towards the heating effects? Like, if you're driving for like high frequency, have you done any, or do you know how to go about simulations to kind of simulate that?
Haven't done any direct simulations of that, but it is an important experimental consideration. But I know there's all sorts of strategies that you can use, say like to make sure that you don't, to avoid heating, to make sure that you don't drive with certain frequencies that correspond to certain transitions in your atoms. You can be kind of smart about the driving frequencies that you choose. And you can also choose so that, there's a paper recently to show that you can reduce these effects of heating by ensuring that when your atoms are heated, they leave the lattice, so they leave the system. And so they're heated and they're sort of evaporated off, and it's sort of like part of the cooling process in some way. So there's all sorts of different strategies that people use, and I think it's, potentially going to be like an engineering problem to figure out exactly how you manage this in the best way, but
I'm not an expert here either, but I've heard very heated arguments about as things scale up particularly, that in analog systems, it's just much, much harder to know how accurately you're doing this simulation. I wonder if you have any comments on that and whether there are advances in that that are worth us knowing about.
Yeah, okay. So, yeah, so you sort of mean sort of like a verification that you're doing what you're saying.
Verification or being able to bound components in ways that people believe that you're putting them together and can get bounds on the overall performance. Yeah.
I think in many cases, obviously for a lot of the systems that have been studied, if there's some sort of way that we can classically simulate what we expect to happen, and then often in these experimental papers there will be a comparison between some simulation and what you're getting in the experiment and showing that it follows the same sort of qualitative behavior. Things like, and then sort of just making sort of sanity checks along the way, like checking, there's ways that you can say like check you're in the ground state because you can measure, you can prepare your system in a certain ground state and you can verify that, and then you can adiabatically change the Hamiltonian and then say, well, we expect it to be in the ground state now, and then you can do measurements of entropy before and after and sort of say, well, this is definitely seems to be staying in the ground state. So there's sort of checks and balances, but I think in the case, I think you're right in some cases it's sort of like a verification thing. I mean, how do you know, if you're doing something completely new that the quantum, like a classical computer can't do, like how do you know for sure that this is exactly the quantum physics and there's no sort of experimental imperfections? I mean, I think that's a good question and something that experimentalists always have to be thinking about. How do you verify these things? But yeah, sort of, and I think this is kind of a problem across sort of like phase if you have like transition across a phase where like you have a gap closing and then you can't verify that it's always going to be adiabatic, then you kind of have a problem there. But so yeah, I think it's a good question. And then I think in some cases there's ways that you can convincingly get around it. But yeah, so in the case of, I know an experiment some people want to do is sort of measure ground states of spin liquids. And I think there's a discussion about how, once they actually build that system, how they're going to actually, they'll measure something, but how are they going to say, how are they going to verify? I mean, yeah, I think that's a kind of an open question, yeah.
We've probably got time for one more, if there is one more.
Have you considered the multiple species case? Like, would you be able to control the hopping individually, for instance?
Yes. Okay, so yes, you can for, in normal case, there's lots of experiments done. In the global case where you don't have this flocade, there are ways that you can engineer different tunnelings for different species. And you do that by using different beams that, if you have like different species and different hyperfine levels, then you can sort of address them in ways that you don't, one doesn't see the beam of the other because the frequency is not right. And yeah, I haven't looked at it directly in the case of this local flocade. I can't see why it wouldn't extend, but probably would need some thought, yeah.
Thank Georgia one more time.